Hello, my name is Matthew Brenneman, and I am an instructor here in the mathematics department at Embry-Riddle Daytona Beach. And I want to welcome all of you to the online version of MA 242. I hope everyone is doing well and they're safe. I know this is kind of an unusual set of circumstances, and I don't know how familiar you are with online courses. Um, Basically, we're going to do a sequence of videos that are going to take the place of regular lectures. This handout, for example, will be made available to you, and your instructor will let you know where you can download it. Some of the font is a little bit small from time to time. And one of the things that you really want to kind of bear in mind is that even though these videos are substitutes for lectures, you can't ask questions during the videos. And so it's really important that you go for help when you need it. And of course, we're going to arrange for office hours and things of this nature. But I just want to really emphasize that you should never feel like you're imposing on us if you need help. Always feel free to, come to us if you have any sort of problems or questions. Um, in these sorts of circumstances, kind of like hurricanes, crazy things happen, and communication is the key to letting us know so we can help you. What I want to do in this video is start off and just go through a light refresher of what we were studying before we left and make sure everyone's on the same page. So to start off with, we're going to be talking about series, and we recall that the word series is just math speak for sum. And when we want to write a sum in mathematics, we generally use what's called summation notation. And so the idea is that if I want to add these numbers, 1, 2, 4, 8, and 16, I might realize that I can write them as elements of a sequence, right? I could write 1 as 2 to the 0, 2 as 2 to the first, and so on. And so I could think of these terms that I want to sum as elements of some sequence, 2 to the nth. And so once I have a kind of sequence representation for the terms I want to sum up, I use the summation notation. And so the way that we read this is this symbol here is sigma, and it stands for sum. So this is a set of instructions. It's telling us sum, and this 2 to the nth is what we call the summand. It's telling us what to sum. So it's saying sum the terms of this sequence 2 to the nth. N is known as the index of the sequence. It's telling us what the position of the term is that we want to sum. Okay, so here this would be n equal to 0, n equal to 1, n equal to 2, n equal to 3, and so on. So n is known as the index for the summation. And basically we have to tell this set of instructions. It's saying, okay, add up these terms 2 to the nth, but we have to tell it where to start, right? So this is called the lower index. Oops. This is called the lower index. I'm going to get it to work, don't worry. N equal to 0. It's telling us start with n equal to 0. And then we have to tell what value of n we want to end the sum at, and this of course is called the upper index. And we dealt with series last semester, so this probably isn't, a great surprise to most of you, okay? And of course we could write this in a sort of general notation. If I had some general sequence a sub n, and I wanted to start off with the n sub 0th term in the sequence and go up to the capital nth term in the sequence, I'd write it like this. Now, it's no coincidence, and we're going to actually explore this analogy further when we get to the integral test for convergence, that series are kind of like a discrete version of integrals. An integral is kind of like an infinite sum, right? We're summing up the areas of rectangles. So this script s kind of looks like this sigma, and our summand, the thing that we're summing, kind of looks like the integrand, the thing that we're integrating. X is kind of like our variable of integration. This index is kind of like our variable. And of course, we're telling it where to start summing and where to end the sum. So this is kind of like the lower limit and the upper limit of integration. Now we want to deal mostly with infinite series. So infinite series just means an infinite sum. And so we're starting at some finite position in the sequence, a sub n, and usually we're summing to positive infinity. And of course, the fly in the ointment is that when we're summing a finite number of terms, the series will always exist, but an infinite series may not. And so to kind of get a little bit of understanding about what this last statement means, we kind of have to look a little bit at what infinite series can do. So an infinite series can essentially do three things. An infinite series can converge. We haven't discussed what that means, but essentially what it means is that this sum is equal to a finite real number. And we're going to see later on this video that if we sum 1 over 2 to the nth from n equals 0 to infinity, this appears to equal 2. And it can diverge. So if instead of 1 over 2 to the nth, I summed 2 to the nth, this thing is going to diverge to positive infinity. And of course, the last thing that can happen is that the sum does not exist. It does not converge. And so if I had something like, for example, the infinite series from n equals 0 to infinity of 1 over 2 to the nth, I'd notice that this thing keeps alternating. As I add terms, it keeps alternating between 0 and 1, and it would never actually equal a finite number. And again, it's kind of worth pointing out that these are exactly the three types of behavior we saw when we looked at type 1 improper integrals. So for example, if we evaluated this integral and you went back and kind of reviewed your formulas for integration, you'd find out that this is equal to 1 over natural log of 2. And if you looked at this improper integral, 0 to infinity of 2 to the x, this does not exist because it becomes infinite. And if we looked at this integral from 0 to infinity of sine x pi over 2, and we applied the criterion for this improper integral to converge, we'd see that it doesn't. Okay. So we have to talk. So obviously we're interested in seeing if this, infinite sum converges, and we have to put a little bit of a finer point on what that means. So when we're talking about the convergence of an infinite series, it's useful to introduce this term called a partial sum. And a partial sum is where we're adding up just a finite number of terms in the series. So if I have some infinite series and I want to look at the nth partial sum, which I'm going to denote by capital S sub n, I'd be adding up the first n terms in the series. And so if we wanted to give a kind of concrete example of this, right, if I was adding this series right here, if I wanted to look at this infinite series, and I looked at the partial sums, S1 would be the first term in the series, which would be 1. S sub 2 would be the sum of the first two terms in the series, which would be 1 plus 1 half, or 3 halves. And S sub 3 would be the first three terms in the series, 1 plus a half plus a fourth, which would be 7 fourths. And so if we have this concept of partial sums down, we can talk about what it means for an infinite series to converge. And mathematically, we know that when we're talking about converging, we're talking about a limit. And so it's not too surprising that what that means is that the limit of the partial sums converges. And so to kind of give you a concrete example of what this means, okay, this example that we're looking at with the infinite series of 1 over 2 to the nth, we could write a little MATLAB code to actually compute the first couple of partial sums, okay? So I could specify some starting index. I wanted to start at 0. So I want to look here at the behavior of the infinite series of 1 over 2 to the nth from n equals 0 to infinity. So I'm going to start off at 0, and I'm only going to look at the first 11 terms. Okay, I'm going to look at the partial sums. So I'm going to end at n equal to 10. That'll be the first 11 terms. And so I'm going to go ahead, and what I'm going to do is I'm going to start computing the terms in this series, and I'm just going to compute the partial sums by adding the partial sum, the previous partial sum, with the new term in the series. And so if we look at this, right, we just saw a second ago that for this infinite series, the first partial sum is 1, and sure enough, if you go to the first partial sum that just has one term, sure enough, it's 1. And if we looked at the second partial sum, which is when we have n equal to 1, we get 1.5. And we look at the third partial sum, which is when n equal to 2, we get 1.75, and so on. And so we can ask this question, kind of based on the behavior of these partial sums, do they seem to converge? So the limit as n goes to infinity of s of n, does it converge? And the answer is that it appears to converge to 2, right? So these are my partial sums, went up like this, and it seems like these partial sums converge to 2. And we're going to prove in the next video that that in fact is true. You have to be a little careful using computers, though. Some series converge very, very slowly, and it can look like they're converging to an actual number, but they don't. So here's kind of the approach we're going to take in Chapter 10. The first question we want to ask is, does an infinite series converge? And to answer that question, we're going to introduce a lot of different tests, okay? So we're going to have some infinite series here, okay? It can start at any place, but I'm usually going to start at 0 or 1, depending on the series, okay? And we're going to want to know, does this converge to some actual number? And to answer that question, we're going to introduce a bunch of tests for convergence. Okay. So we're going to have something called an integral test, a ratio test, a root test, and so on. And of course, not all these are going to work. And so the big challenge is going to be, which test do we use? And so the idea here is actually kind of similar to when you were doing integration, right? So you had these integrals, and we had all these different methods for evaluating integrals, right? So, you know, we had u sub, trig sub, you know, trigonometric integrals, partial fractions, okay, and so on and so on. And notice that how you made that decision was you looked at the form of the integrand, right? So if, for example, I had an integrand that looked like this, you might say, I have a composition of functions. I have the derivative of the inside function in the numerator. I'm going to try u sub. And we're going to do the same thing here. We're going to look at the form of the summand when we're looking at an infinite series. So if we see 1 over 2 to the nth, we're going to notice, based on the form of the summand, in the same way that we use the form of the integrand, that, hey, we could use the root test here. Now, it's important to understand sometimes there's more than one test. For example, I'm sure that a lot of you looked at this and said, hey, I could use trig sub. And sure enough, it's going to turn out that in this case we could also use the ratio test, and we're going to kind of explore this more, okay? So we're going to see sometimes there's actually more than one way to do it. But the key is to find one way, and again, that's going to be based on the form of the sequence terms. And of course, the next question we're going to want to ask is, if it does converge, what does it converge to? And in the next video, we're going to actually look at an infinite series that we can evaluate, called the geometric series.